Hello, in this video we're going to integrate a rectangle in polar coordinates. And really I'm doing this because some of the research that I'm doing, I had to do this. I had to integrate a rectangle in polar coordinates. And so I had to look it up to make sure I was doing it right. And I was like, well, that'd be a good video. So if this is our region and this is our function that we're integrating over this, the standard way to do it is pretty straightforward. You plug in f of x, you integrate from 0 to 1, and 0 to 1, it's this. So you plug in this. And then if we do in regards to x first, so it's x squared over 2, plug in the values, we get 1/2, which is this. And integrate that, we get y squared over 2, but the 2 goes into there, so it's 4. And plug in our values, we get 1/4. And so it's a pretty standard or easy integration. But let's convert it to polar coordinates. So let's let x be r cosine theta, y be r sine of theta. The Jacobian would be this, which that's the determinant. You get r. Now we want to plug this in here. Okay, so this is the tricky part. Okay, so here is our region, and theta is easy. Theta goes from 0 to 2 pi, right? But r is the tricky part. When we're between 0 and pi over 4, r is, follows this path. And then once we get past pi over 4, then r, the radius, starts following this path. And so really, we're going to think about this in two pieces. So if we integrate this from the lower part and then add it to integrating the upper part, and that's what I'm attempting to do here. So if we look at this bottom piece first over here, this is 1 and this whole side is 1. Right? Because we're integrating this triangle. Now, the length of r is, if we call this cosine, r is going to be 1 over cosine of theta, right? Because cosine of theta is 1 over r, and then you manipulate, you get this. Now here, in this piece, it's a little different, okay? So, this angle here, if we generically call it theta, but we're between pi over 4 and pi over 2. If this is, it cuts, so that's this theta is actually this piece. And so the sine of theta for this triangle is 1 over r. So then you solve for r, you get r is equal to 1 divided by the sine of theta. And so now we take those pieces of information and we do our integrals. So this is actually the right integral, the lower triangle, and this is the upper triangle. And so when we put it, remember it was x times y, and x was, so this is x, so it's r times cosine of theta, and this is r times sine of theta. So there's r squared, but the Jacobian is r, so it comes in as r cubed. And the same thing over here. So now we integrate with respect to r first. You get r to the 4th over 4 on both of those. You plug in your limits of integration. You get this. Now we do u substitutions on the bottom piece. So the use on this one, it's the u sub of cosine of theta, and then we get du equals minus sine of theta d theta. And then over here we get, and I left out a d theta, so we get this, which is, u, we let u be sine of theta, and du is equal to cosine of theta. So when we plug it back in, we get this. So it's minus 1/4 u to the 3rd, 1/4 u to the minus 3rd. we integrate this, we plug in our limits of integration, we get this. So here, you know, it's this, and then it's minus, and then plug in minus, and you get 1/8, and then here, of course, you plug in 1, you get -8, and then it's minus, plug in this, you get this piece, and when you add those together, you get 1/4, which is what our original integral was. Now, of course, in this example, it's a little silly to convert it to polar coordinates, but I wanted to illustrate this, so in a couple videos, I will point back to this as a background video. Well, anyway, I hope you enjoyed that. I did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.